好，咁就好歡迎咁多位啊！即係我哋應該係如果講香港天文學會搞嘅講座咧，咁其實應該今次嚟講咧係我咁多年啦，即係入咗會以嚟咧，應該見過係最大棚㗎啦，基本上嚇，因為我哋今次有80至100個位咧都 full 咗啊，咁啊有啲都仲要候補咁啊，但係都唔理㗎啦，即係候補都唔夠位都可以企喺後邊都 OK 嘅嚇。咁咧就今日好歡迎大家嚟到啦，咁就我哋好榮幸咧，就邀請到咧，即係應該在座有好多朋友都認識嘅，一位咧就係、是、業餘嘅人士，但係影相咧就或者影月球行星咧，咁就係去到專業級㗎啦，或者係一個研究級嘅朋友啦，咁就係 Christopher 高啦嚇。咁大家有冇人係聽過 Chris 嘅名㗎？有冇人喺 Facebook 度見過佢啲相啊？係咪好震撼啊？係嘛？咁啊，即係有好多，如果有影開咁你而家大家見到在座呢一個咁嘅 slide 啦，係嘛？咁你都見到咧，其實全部都係啲作品嚟嘅。咁以下落嚟咧，佢會用少少時間咧就去詳細介紹啦。咁但係咧，因為 Chris 咧佢係菲律賓人嚟嘅，咁咧所以咧佢係講英文嘅，咁所以咧我哋就要由呢個 bilingual 咧就轉做英文啦。咁所以我哋咧就會做一個簡短嘅介紹Chris 好嘛？咁等大家了解，然之後佢就可以開始㗎啦。Okay, Chris, let me have a short introduction about your profile before your presentation. Okay, so actually, Christopher has been an amateur astronomer for almost 30 years, and his main interest, I think many of you already know that, is focusing in the lunar and planetary observation, and he is usually using his C14 Schmidt Cassegrain for some high-resolution imaging, as you see some of the pictures here, for example, the Mars and the Saturn, and also you see his telescope on the astrophysics mount. And in 2006, as an amateur astronomer, he got a very remarkable achievement by joining the Hubble Space Telescope team to observe the Jupiter. And also in 2009, he also joined the Hubble Space Telescope Heritage team to image the cold transit of the Saturn. And there was quite an impressive result, as some of his images have been widely published in some well-known international journal, in particularly for some really scientific one, for example, the Nature. You know, as you may already know, that even for the professional astronomers, it's not that easy to publish this kind of the images in such kind of the high-ranked journal. So this is quite a remarkable achievement. So in order to recognize his long-term contribution for his planetary observation in the past decade, the Association of the Lunar and Planetary Observers in the United States awarded him as a HKAS award. And later in 2015, the International Astronomical Union has designated asteroid number 30100 permanently named after Mr. Christopher Gold. So I think after such a brief introduction, you will know Chris, and although he always claimed himself as an ordinary observer, but we always said that he's already professional, but work as an amateur practice. Okay, so ladies and gentlemen, may I have the greatest honor to invite today's invited speaker, Mr. Christopher Gold, to conduct the lecture. The title is From ToUccam to Hubble. Let us take out.
Good evening, everyone. First of all, I'm happy to be here. I'm always happy to be here. First of all, I'd like to thank Eric. You know, for one thing, I learned to image planet because of this guy. So this guy is a real master. I'm just lucky because back home we have good seeing. Anyway, my talk is about from ToUccam to Hubble, Adventures of a Planetary Imager. Well, you know, it's not always when ordinary people like us can contribute to science, but one thing about planetary imaging, it's one of those science where amateurs really contribute a lot. You have to bear in mind that most professional astronomers have limited access to Okay. Most professional astronomers have limited access to the Hubble Space Telescope, even ordinary observatories. In the, in the pecking order of things, planetary astronomy is way down below in priority compared to other parts of or other studies of astronomy. When we're imaging planet, we're actually doing one thing. We're fighting the atmosphere. People were asking me, what's the best place to image planet? Is to get out of the atmosphere. Unfortunately, it's not an option for us to remove the atmosphere. So basically, we just try to live with the atmosphere. Now, there are three ways, of course, to get the best planetary image. The first is getting out of the atmosphere. So that's why we sent some spacecraft like Hubble. James Webb is coming up. And there's also Kepler up there. But the thing is, it's difficult to get Hubble time. And also, it's also very expensive. The next is adaptive optics. Adaptive optics is using an artificial star like this laser and having two telescopes, one telescope observing the deformation of that artificial star and some mechanism underneath the second telescope to compensate the defects of the atmosphere. This technology has been used, actually this was invented by, since the 70s, but it was classified because it was developed by the National Security Agency of the United States. They use it not for astronomy, but on their satellites to look down to Earth. Now, this technology was declassified I think in the late 90s, and is currently used by, I think, 3 observatories: Gemini, Keck, and VLT. Now, the problem with adaptive optics, I actually got to know this guy. He lives in San Diego. He works for the NSA, and he developed adaptive optics. The problem was the price for an adaptive optics system is around $50,000, so which is way, way, way beyond the budget of most of us here. Of course, the last option that we have is lucky imaging. Actually, originally this was called spectral imaging, but right now it's called lucky imaging. Now, lucky imaging is basically taking a video of the planet. A video is basically a set of images. So by using high-speed cameras, we're able to basically freeze the atmosphere. And with free software that basically picks and chooses the good and bad images, then we have a package that really helps us. So the development of this is, of course, due to, first of all, inexpensive devices, cameras. And also, the most important is the development of computer hardware interface. How many of you remember the serial port or the parallel port? Can you imagine before? We used to have a serial port where I think the original serial port before the UART was 300 bits per second. And what do we have right now? We have USB 3.1, which is gigs of data per second. So in fact, I have a camera actually back home, which I use right now, that my hard drive, my SSD cannot keep up because it's just throwing so much data. It's a 5 megapixel camera that basically goes as high as about 100 frames per second. So it pushes data close to about 350 to 400 megabytes per second. So it's with the new interface, it's really amazing. Of course, we have faster computers, and also, most importantly, the development of software, free software. We have AutoStacker, we have Registax, we have Fire Capture. I'm really amazed with these programmers. They have their jobs, but they give away these softwares for free. And it's I really salute the authors of these softwares. They did a good job. Now, of course, when it comes to telescopes, as they say, the bigger the better. So when it comes to planetary imaging, the bigger the telescope, the better. Now, actually, Hong Kong is one of the best places to image planets. If it weren't for those smog you have there up north, the best place really is on an island where you're surrounded by a body of water, where you have luminar flow and laminar flow. So basically here in Southeast Asia, the closer you are to the equator, of course, the planets are higher. The closer you are to the water, so you have more stable atmosphere. Probably in Hong Kong, if you have wind from northeast, east, all the way to the west, as long as the wind comes from the water, you should have good seeing. Of course, it's another story if it comes from the north, because it not only brings the bad seeing, but also all the pollution you can get. Now, the camera, when I started imaging, and I couldn't forget, I kept on emailing Eric before, trying to learn the ropes. We started with a humble webcam. Of course, the webcam is cheap. During that time, the webcam was only USB 1.1. And, webcam is supposed to capture videos to, push to the internet. So, if you're pushing to the internet with a limited bandwidth, you try to compress the data. So the problem is when you have compression, you lose a lot in the details. So there is another source of camera, and these are the machine vision cameras. These are actually the cameras used by factories to do their, quality control, quality check, high-speed manufacturing. So these are the cameras, and we are getting actually cameras from these companies and use it for planetary imaging. But of course, the difference, these are a little more expensive than the webcams, but they have lower noise, and of course, faster interface, zero compression. I just want to, if any of you are using Windows 10, please do not upgrade to the anniversary edition. Because it will kill your camera. Microsoft right now is so brilliant that they think that all cameras, including industrial cameras, have to go through compression. Not only that, it has to have a fixed frame rate. They want to turn all cameras into a webcam. And right now, in fact, even the webcam, a lot of webcams don't work after the anniversary edition. This is the edition of Windows that was released on August 2. I was so stupid that I updated this, and my camera doesn't run in this computer anymore. And thankfully, I still have another computer that I didn't upgrade, so I'm using that now. But if you're using Windows 10 and you're doing imaging or even webcam or doing anything, Microsoft broke Windows 10 anniversary. In fact, my wife was furious because it also broke our payroll software at work. She wasn't very happy with that. And during payroll, I mean, you can see she was very furious. So next time, if Microsoft releases a new edition, wait for about 3 to 4 months before deciding to do anything. And of course, right now we have a lot of cameras available. Some Celestron, Point Grey, ZWO. And of course, there's also QHY. One thing amazing about these cameras is they have very high frame rate, no compression. Right now, most of the cameras are USB 3 now, at least USB 3. Of course, there's a lot of question now, which to use, color or monochrome? I would say, if you're a beginner, go for color. But you need this accessory called an atmospheric dispersion corrector. Now, one problem with color imaging, when you're imaging with a color camera, if the planet is below 70 degrees altitude, the color tend to separate it's called the atmospheric dispersion. So the red, green, and blue, if you look through the telescope when the planet is low, you'll see fringes of blue and red on each side. This is atmospheric dispersion. This will correct atmospheric dispersion. In fact, the lower the planet, the worse the dispersion is. So with this accessory, it's not really that expensive. I think ZWO is selling this for $100+, which is actually pretty good because before, this type of accessory would cost thousands of dollars. So, I mean, US, not Hong Kong. So, right now, this accessory is necessary. But if you want the highest quality image, going monochrome is the way to go. I remember before, my wife thought I was crazy because I was, when I had a ToUccam, I had to remove the color chip and change it to black and white. It was like, why the hell are you doing that? Who would want, example, can you imagine if you say, I'm going to change my color TV into a black and white one? Everybody will think you're crazy. But, one thing, you have to understand how the chip works, the imaging chip works. When you have a color cam, they actually overlay a filter called a Bayer filter over the chip. So basically, there's a little light loss on it. So basically, monochrome cameras basically have a little higher sensitivity compared to a color cam. And another advantage of the monochrome camera is that you can get better color fidelity with a color cam, with a monocam than a color cam, because most of the filters used by the cameras are not pure RGB, but sometimes RGG, because they use actually 4 filters. But the problem with color cam is it's also very expensive because you have to get a filter wheel and the filters, and these are sometimes more expensive than the camera itself. But if you want the best, really, it's and you don't need this accessory, the atmospheric dispersion corrector, when you're using a monochrome camera. Now, thankfully, right now, CMOS is the king. I mean, CCD. Right now, there's I think the king of chip right now is the IMX290 by Sony. This is a back illuminated CMOS chip. So this is very, very high sensitive chip. It's not featured here, but it's actually very sensitive in IR, very high sensitive in IR, and it goes to a QE of about 90%. So right now, I think ZWO and QHY are selling cameras of these, the IMX290, and basically this is I would say, the best camera for imaging planets right now. Now, in my case, one of the biggest life changes that I experienced was discovering this little red spot called Red Spot Junior. It was funny because during that day on September 20, it was actually September 25 or September 24 Universal Time, but September 25 here in our local time, Hong Kong, Philippine time. I was supposed to wake up at 4 o'clock in the morning, but and I don't know what happened. I didn't hear the alarm. The next thing I knew, when I look at my watch, it was close to 5. And I wasn't sure whether to image or not, but I went ahead to image Jupiter. In this case, I use a borrowed C11 using a DMK21 from the imaging source. And when I took the image, you have this, this used to be a white spot, oval BA, has turned red. You'll notice that at this image, this spot is still rising. So, in a sense, if I had really woken up at 4 o'clock, I wouldn't have made this discovery. So, it was really a lucky discovery for me. One thing nice was that a few weeks later, I received an email from Dr. Imke de Pater from UC Berkeley asking me, do you want to join our team? We're going to use the Hubble Space Telescope to image Jupiter. I said, oh, wow, of course. So I became part of their group, and our group basically used the Hubble a total of about 60 orbits. Now, how does Hubble work? Now, Hubble is, of course, an orbiting satellite. The program of Hubble, what it's going to do is automatic. It's uploaded at 0 UT every Sunday at 0 UT. So the whole week program of Hubble is basically programmed on a weekly basis. So after it's programmed, nobody can stop what it's doing. It'll just go through and run through the program. Now, depending on where the object is, you have what you call an orbit. An orbit time will range from about 15 minutes to about 52 minutes. Basically, the orbit is when the space telescope is pointing at that object as it goes around the Earth. Now, this satellite goes around the Earth once every 92 minutes. Now, there's only one thing that it cannot do. Actually, two things. Number one is point at the sun or point close to the sun, or point at the moon or close to the moon. In fact, during our first orbit of our first try, this guy, Mike Wong, his dad is actually from here, Hong Kong, forgot that Jupiter was close to the moon, and during the slewing time, we actually caused the spacecraft to go into safe mode. So we were so nervous. Oh, we're gonna damage the spacecraft, and it's all our fault. So and actually, it wasn't the first time. Mike Wong was also the one who basically almost destroyed the imaging chip of Spitzer, the infrared satellite, because he tried to point Spitzer at Jupiter, then finding out that Jupiter was actually too bright that it almost burned the CCD. So, these things happened. So this is our first image of Red Spot Junior, or the Red Oval BA, using the Hubble Space Telescope. During that time, we were still able to access the advanced camera for surveys, high-resolution camera. Unfortunately, this camera actually died. Basically, the power circuit burned, actually side A and side B, which was really very sad, because of all the cameras inside Hubble, this was the most high-resolution camera. This was used for the deep space, those deep galaxies. This was the camera used. Unfortunately, it's kaput right now. And so we're right now using WFC3. So the next, this is an animation made by one of our group, Sylar S.I. Davis. This is how the storm moves. Basically, this is an animation. This isn't really a real. Wait a minute. This is a simulation. Okay, this is a simulation. Very few people have seen this because we haven't made this public yet. But this is how the storm is. What is this? This is actually an anticyclone. So this storm is a high pressure storm that really pushes up into the atmosphere. We're hoping that JUNO will have the opportunity to pass through this storm and observe it. But right now we're still trying to finalize the orbit of JUNO. This is another run that we had. There was actually a third red spot of Jupiter that appeared temporarily. Unfortunately, this red spot went between the two red spots and basically was destroyed. So this happened in I think 2008. Yeah, 2008. This is an image of Jupiter using the Keck Observatory. This is an example of an image of Jupiter using adaptive optics. So it's actually incredible. The resolution is incredible. Especially, of course, this was done with a 10-meter telescope. So this is the global image of Jupiter. This is done by Mike Wong. Basically, we had about almost 10 orbits to make this global image of Jupiter. Another thing that we did was, I wonder if you've seen this image, the quad transit of Saturn. So during, what was it, I think 2009, 4 moons went across Saturn. This is 1, 2, and 3, and 4. So it was kind of incredible to see 4 moons. This is a very rare event. Unfortunately, this thing would be difficult to image using amateur instruments. So we went, I shot an email to Mike, can we image this with Hubble? At first I didn't know where he was because I knew him, he was in UC Berkeley. then he sent me an email telling me, oh, I'm working with Hubble right now. I got you 4 orbits. I said, wow, okay. So we were able to get 4 orbits to get this image, and yeah, this is one of the few times that I was able to instigate an image of using Hubble. So this is another image. This is a ground-based telescope. This is an eclipse of Io on Ganymede. This was taken with an 11-inch telescope using the old EMK21 F04. I have a newer image which I took about, I think, last year. I think I posted it last year, but this was really spectacular. So it's something, it's an extraordinary eclipse. Now, one other discovery that I made was in 2010, when there was an impact on Jupiter. I wonder if you've heard of this, on June 3. The year before, in 2009, Anthony Wesley discovered an impact remnant on Jupiter. Now, the following year, on June 3, there was a press conference in the US, publishing the result of that impact. And coincidentally, while they were doing the press release, Anthony was in, I think, in Adelaide, a Broken Hill. It's a town north of Adelaide. While he was imaging, he captured a flash on Jupiter. And coincidentally, I was also imaging at that time. It was a normal night. It's not a night you would say, oh, I'm going to discover something. So I just took an image, and when I saw in the internet that, I was able to see an impact, I asked Anthony, what time did you see the impact? And he said, oh, around this time. Oh, I was imaging at this time. Let me check. So when I was checking the video, this thing came out, and boom. I was screaming. Now during that time, I had a 2-year-old. When he saw me screaming, he started crying. He thought I was angry. But the thrill of the excitement of the discovery, it's really something. I'm talking about. I want to emphasize this one is because, I wonder, you've been following the Facebook about the recent iPod fiasco, where you have this Spanish guy tried to pass off an image of Mars as his own, even though the resolution was that of the Hubble Space Telescope. Basically, he stole the image of the Hubble Space Telescope and said, I took it with an 11-inch to 12-inch telescope on the ground, and he got the iPod, and we exposed that it was fake. There's this thing of getting better and better images. In my case, I take an image. If it's good, it's good. If it's bad, it's bad. I post everything. But what really gives me the thrill is the thrill of discovery. The first thing I do when I get the image is to basically analyze the image. Look at the image. Is there a new red spot? Is there an impact? Or if there's any new feature that's going on in Jupiter? Rather than, you have to get the most beautiful image. And this is the danger. When it's not about the science, it's all about the beauty. There's a tendency to overdo things, and in some cases even fake it. So we have to be very careful with that, because that's basically what happened. And the sad part about this guy, I feel sorry for this guy, because basically he was very popular in Spain. Right now he lost everything, and we found out that a lot of his images were he actually stole images from other imagers, including me, and some from Australia, and made it his own. And one thing which really terrifies me is that, example, right now, we have a joint venture, or basically a collaboration with NASA to support the JUNO mission. And when we have these fake images coming in, it's going to poison the data that we have. Because one thing important we have with our data is not only the planet itself, but the times. And most of this is how we're doing with the JUNO support right now is we have these images, we send it to JUPOS, I wonder if you've heard of JUPOS. It's actually, I'm also, these guys, I salute these guys. These are ordinary people, they're not astronomers. The only people, what they do is all the amateur images they get, they make measurements, and in the end, they can make a graph of the motions of each interesting objects in Jupiter. And that's what they do. For free, no one's paying them. And basically, the thing is, if you get bad data in, it's going to poison the long-term outlook. And not only that, the professionals are going to lose confidence. So basically, what's more important is not to have the most beautiful image, but you have to publish the data and, the thrill of the discovery. There's this guy in Iran. His images, I would say, are below average because of the turbulent conditions that he have. But he keeps on publishing images. And coincidentally, he was the first one who imaged that huge storm on Saturn. He was the discoverer of that storm. So that alone is something very big. So it's not about the final quality of the image, but basically getting the data in. This is one thing nice about when you have the first time we had an impact is that we can easily get the cavalry. We're able to get the Hubble Space Telescope. This is the very large telescope in Chile, and Gemini. I think, Gemini in Mauna Kea. So all these are adaptive optics, and this is Hubble images. We were trying to find remnants on the impact. Unfortunately, there were no remnants. Then we discovered that it was just a bolide. Anyway, it's more or less like the one that exploded over Russia in Chelyabinsk. So basically, what hit Jupiter was something like that. And ever since Anthony and I made that discovery, there had been, I think, 4 or 5 other impacts that have been discovered. It seems like we can discover an impact every 1 or 2 years. So if you're imaging Jupiter, make sure you keep your raw data and run it through a software called JID, because who knows, you might win the sweepstakes. Another thing that I did, this is, I would say, this is also a big discovery for me, was the revival of the South Equatorial Belt. Now, once every few years, what happens is that the South Equatorial Belt of Jupiter will disappear. In fact, it's like this, it turns white. It's kind of weird because when you look at Jupiter, normally you see 2 belts of Jupiter, then suddenly it becomes white. One thing about this is that the revival, the astronomers have been trying to figure out how the revival works. And twice, in 2007 and in 2011, I discovered these outbursts. These plumes that erupt on Jupiter, and basically these outbursts would signal the revival of the South Equatorial Belt. One thing interesting was that on 2011, again, after I made this discovery, we were able to get the cavalry in. We were able to get KEK and IRTF, and you can see the outburst there. It's really incredible to look at it. It's something powerful just erupted inside Jupiter. Quite frankly, we don't know what's inside Jupiter. That's why we have JUNO there. So basically, this is the fun thing about discovery. When you're imaging every night, sometimes, on the days you don't expect anything, that's when you make a discovery. And here's another more image of that outburst. You can see how complex that outburst became. So from that tiny outburst, it became something like that. It's really nice to see, professional observatories observing what amateurs discover. And this is one of my last image of Hubble. I wonder if you've seen these images. Actually, this is an example of a Hubble image that uses amateur processing. Meaning, in this case, I use derotation, I use amateur sharpening. So these 2 images, at first the professionals tried to process this image, And I'm part of the group that basically used the Hubble to take these images. And when I got the raw data, I just posted it, hey, what do you think of this? The professionals said, they threw out their image, oh, we're just going to use this for the press release. So in the end, these two images have been used many times, but I was the one who processed these for them. So it's kind of nice for us amateurs to basically help using the tricks that we use in our trade to support the professional astronomers. And I'm also doing some work with the Thai National Observatory. These are two images of Jupiter using the 2.4 meter Thailand National Observatory. And you can see that, yeah, it's incredible. We can actually do ground-based color image with large aperture telescope. So hopefully we can build one here in Hong Kong, bigger telescope. Probably better if we place it on those outlying islands in the south. But yeah, it is possible to do extremely detailed ground-based color images of Jupiter. Now we come to the part of the JUNO mission. I hope that a lot of you would keep on imaging Jupiter, because the JUNO mission really needs our help for them to know what they're doing. Anyway, I'll explain it to you. So this is a JUNO spacecraft. What is the primary objective of the JUNO spacecraft? It's not actually to image planets. In fact, when I discuss JUNOCAM, you're going to laugh at what they did. It's actually crazy. But the main instrument is this gravity sensor. Now, this gravity science is none other than the high gain antenna of the spacecraft. So what will it do? As it gets to the close orbit of Jupiter, it will start transmitting data to Earth. As it transmits and as it moves through Jupiter, the changes of gravity in Jupiter will push and pull the spacecraft. And as it does that, there will be a Doppler effect on the radio waves that reaches Earth. And from that, the astronomers here on Earth can do a gravity map on Jupiter. Okay. So these are the objectives of JUNO. First of all, we want to know what's inside Jupiter. As I said before, we have absolutely no idea of what's inside. This might or might not be true. Jupiter we don't know how big the core of Jupiter is, how mass is distributed inside Jupiter. And one thing about the most intriguing part of Jupiter, we know its inside is mostly hydrogen, but it's not gas, but fluid. And as it rotates, it creates the magnetic field. But having a fluid metallic hydrogen, a fluid hydrogen is like mercury. Mercury, it's like liquid metal. It's really liquid metal. But it's something that we cannot imagine. So hopefully, as JUNO gets through Jupiter using the gravity experiment and the magnetometer, we can basically map up what's inside Jupiter. So this is the possible interior of Jupiter. But again, these are just what we think. It's funny, I remember a few years ago, I have a book, it's funny, it's about bright planets. These were images of planets taken by the Lowell Observatory. And when I read the Mars section, it's kind of funny because when you read the Mars section, they were talking about vegetation. This was in the 40s, 50s. They were talking about vegetations on Mars, seasons of Mars. They even had crop reports on Mars. And when we sent this first spacecraft there, it was like, oh boy, were we wrong. And I think the same thing's going to happen when you look at this about maybe next year. You're going to laugh at this one. So basically right now, this is what we think the inside of Jupiter is. But I'm sure next year, we're going to have a very different picture of what Jupiter is. And just as about 60 years ago, before the first spacecraft went to Mars, they were having, basically annual crop reports on Mars, vegetation reports. In fact, you have the canals of Mars. So you can just imagine what it'll be when JUNO will start its work. So another important mission of Jupiter is basically looking for water. It's not really to find water, because we know there's water in Jupiter, but how much water, the water ratio of in Jupiter, of the Jovian atmosphere, how much water is there, the percentage of water in relation to the atmosphere. Hopefully we'll find out, because we believe that Jupiter is primordial. So basically what percentage of water there is on Jupiter will basically reflect on the solar nebula that form the solar system. So finding that out will be very, very important for us. And also with what they really want is using the radiometer to probe deep into Jupiter. But for us amateurs, what we are really involved with is JUNOCAM. Now, JUNOCAM is on the side of Jupiter. It's over here. Now, how does JUNO orbit Jupiter? Now, I wonder if there's an orbit here. Actually, JUNO is going to have an elliptical orbit on Jupiter. So most of its time, it's outside Jupiter. Why doesn't it stay close to Jupiter? Because of the intense radiation of Jupiter, this spacecraft won't last 1 week. Okay, it will just plunge into Jupiter for 2 hours and it goes back out. And one thing interesting is, number one, it has solar panels, which means these solar panels has to point at the sun at all times. So the way it orbits is that as it gets close, it will get close at the terminator of Jupiter. So it will basically hug. Now, you'll notice that the spacecraft is spinning. If you were here earlier and saw the video, you can see the spacecraft spinning like a pinwheel. It actually spins once every 3 times in 1 minute. And it will have, this is the field of view of JUNOCAM. Small, narrow field. This is the reason why they're asking for the help of amateurs. Because with just that image, they don't know the hell what they're looking at. Because it's just very, very tiny spot there. They need a big picture that we provide. So they can make a sense of what they imaged. It's actually, this camera is so complicated. Oh, this is how JUNO will orbit. Notice it will face this way. And it will go around and around and around. When it gets to stable orbit, it will go around every 2 weeks. Okay? So the orbital period is 2 weeks. And it gets close, then it will shift there. Gets close, notice. We're the sun. So it's imaging at the edge, at the terminator. So this is how it goes. Now, things get complicated from here. This graph over here is the filter configuration of the camera. I mean, if this were the whole chip of the camera, these slots here are the filters. It's crazy, but that's what they did because they had low budget. In fact, the first time I saw it is like, how the hell are you going to make a color image? It's going to be a challenge because each frame will have a strip of red, green, blue, IR, methane band. It's when we were at Nice and they showed this configuration, I was like, what were they thinking? have you noticed the images of Jupiter? They have those tiny Jupiter. If you look closely, the color is very weird. Because what they did was, as the spacecraft spins, they actually tried to catch it here, Jupiter here red, and they ship it here green, blue, and just try to integrate it. But the worst part is when you're doing the close orbit, like, you know, when you're doing it here and it's spinning, and this is the image, so this slice will be red, this slice will be green, blue, you know, that's how it will be. So you guys have to think of a plan, because when they said that, oh, we're going to have the public process this, they said, wow, that's going to be one heck of a job. Because basically what you have to do is basically probably cut this out and hopefully do a red mosaic from other image as the spacecraft moves around Jupiter, and hopefully they'll be able to catch, you know, some areas green, you know. Possibly we can basically regenerate a color image. But you know, this thing is so complicated that for me, I haven't figured out what I'm going to do if I get the raw data. I mean, it's, you know, if you're going to do a color image, it's going to probably take you days to get one color image. And there's another problem. You know, as JUNO goes around, it's only limited to 80 megabytes of data to transmit per, they call it JUNO, what you call it? You know, for each close approach to Jupiter, there's a budget of only 80 megabytes. You have to understand that we don't have a DSL connection to Jupiter. So because of the large distance, you know, the radio waves, I think it's only about less than 1K per minute, the transfer rate. I remember before, you know, remember last year when New Horizons arrived in Pluto, everybody was demanding, oh, where are the images? Where are the images? Why does it take so long? Because the spacecraft is so far away, it takes time for data to come to Earth. But because of you know, the limited nature of JUNO, we're only budgeted 80 megabytes per perijove. That's the term, perijove, or for each close approach to Jupiter. There's another problem in that we do not expect the JUNO-CAM to survive beyond 8 orbits. Why? Because of the intense radiation of Jupiter. The problem with Jupiter is that the radiation is so strong that it will burn the electronics. If it goes beyond 8 orbits, then we're lucky. But if not, yeah, that's the problem. Okay. How do you support JUNO? There's actually a website. This is the website. You can, for most of us here, we can actually support JUNO by imaging Jupiter and posting the image. So these are the 4 things that we can do. It's image, discuss, vote, and process. Of course, image, a lot of us are doing imaging. The problem I have with the discussion part is that, you know, there's a lot of crackpots that join the discussion group, because one problem they opened the discussion group to the public. So everybody who has a crazy idea is there. And I said, after looking at it, never mind. I haven't even bothered to join the discussion process. So basically, I concentrate on imaging. So the first thing that you do is you sign up. This is how you sign up. Of course, it's free. And yeah, I feel sad that why do I have to be at least 18 years old to image? I mean, no, if a 15-year-old were to image Jupiter, I would be very happy. Or a 12-year-old. But, you know, this is the US government with all their crazy policies, so. What are the filter requirements? So basically, they want the same filters that JUNO had. So RGB, methane band, and IR pass. So you can get these filters quite easily now. Now, one thing about NASA, they don't like JPEG, so they would require bits or PNG. And please save on WinJuPo's file name convention. You can do this when you're using file capture. You go to settings and basically when you're using file capture, don't forget to check this. Why is this so important? Although I have to admit, using this will drive you crazy because the file names will all be numbers, date numbers. You don't even know what you're trying to capture. But one thing nice about this, when you're doing derotation, when you open the file, you don't need to enter the date and time anymore. So it's automatic. The less prone to mistake during derotation. So if you can check this, forget about the rest. Just check this button, WinJuPo's file naming. And it is this file naming convention that is required by the JUNO site. Okay. So this is WinJuPo software. Again, this is a free software. This is basically used for image measurements and basically, the position of each the ephemerides. I would recommend you download the software, if you're doing planetary imaging, because the technology of derotation is one of the most important advances in planetary imaging. Again, this is how you upload the data. This is the screen. Normally, I'm trying to work with the guys doing the website because most of these are redundant, like date, date and time. These are automatic, but other data like your position, the CM123, these could basically automatically be computed. And one thing about this is that the more inputs you have, less people are going to upload. In fact, to be honest, in my case, all I do is just upload. I don't even bother filling these up. So I would encourage you to upload your data, even though you don't have to fill up everything. Like observer longitude and latitude, you already filled this up in your profile. Why do you have to fill it up again? I mean, I don't understand. I've been telling them to simplify the process, so to encourage more people. But I'm just encouraging you, just upload your data and forget about these other details. The next part, of course, is the discussion part. Initially, the thought of having the discussion was to have an intelligent discussion on where to point the camera. But as I said, right now it has basically degraded into a crackpot session where people have their ideas of aliens and whatever is inside Jupiter. So I don't know how NASA's going to deal with it. Oh, by the way, the company that made this website was also the company that made the website of Taylor Swift. So, The last part is the voting part. Again, as JUNO orbits Jupiter, I said earlier, there's a limitation of 80 megabytes. So they're gonna propose certain areas of Jupiter for each perigeo where the spacecraft can point. NASA is trying to ask the public to vote. I would rather that they should have asked the scientists. As I said, I would encourage you to vote because I know you guys are more intelligent than the rest of the other people that have joined the discussion to vote on whatever interesting features there are. Because I'm also excited to see what's these things very, very close up. Oh, by the way, the reason why I'm the next part is actually confidential. So I'm just showing it to you. I'm actually not allowed to show this outside the United States. So this is the schedule for the please don't take a picture. You'll get me into big trouble. Anyway, these are the peri-job schedules. So these are the dates where Jupiter will get close. You can write it down. Anyway, so you'll know when. These are the most important dates, I would say, the first 8 or these up to basically January. This is the test orbit. The first orbit, actually, it's not here. Oh, okay. The first time after the orbital insertion that Juno is going to get close to Jupiter will be on the this week, this Saturday, 27. Is it August 27? Yes, this August 27. But this is all basically instrument checkup. So they're going to make sure all the instruments are running, and also they're going to see how the camera will work. Then these are the succeeding orbits: October 16, November 10, these dates. So I would encourage you to image Jupiter close to these dates, and because these are the important data. I have to say that October, November, December, these are difficult times in observing Jupiter because it's still very low in the sky, and of course, unlike me, where every day is about 25 to 35 degrees centigrade. As it gets to December to January, it gets cold here. It's kind of difficult to wake up early, but hopefully I can encourage you to please come out and image. Please write it down. Don't take a picture. So these are the dates. Of course, the sad day is the orbit 34, which is on October 16 next year, where Juno, unfortunately, is going to crash into Jupiter. So, of course, as you saw in the video, the reason why we want to crash Juno into Jupiter is because we don't want to contaminate Europa. Because we think that there might be life in Europa. So, and of course, those building the spacecraft have microbes all over that spacecraft. So we want to make sure that there's no contamination. You got it? Okay, as people are writing down, if you have any questions so far, please let me know if you have any questions. Yes? Basically right now, basically Juno is in business now. During the times when, during JOI, I was able to use the 100-inch Hooker telescope in Los Angeles, Mount Wilson. Now, it was quite emotional to use this telescope because this telescope is basically the telescope to discover the Big Bang, or basically first observe the Big Bang. This was the very telescope that Edwin Hubble used to see those galaxies flying away. This was the telescope used to image the Cepheid variables of Andromeda during that time, nebula. Then they found out that it was not a nebula, that it was a galaxy, by measuring the Cepheid variables using this telescope. So this telescope was quite historic, and this is the image, the methane band image. It's not really that great because you have to understand that while we were imaging Jupiter, Jupiter was only 30 degrees above the horizon. But we were happy that with what we were able to get. This is 100-inch, so it was quite interesting. You'll notice there's a refractor. There's actually a Meade refractor over here. Actually, the light goes from the mirror, then goes to a cooled focus, then goes through this refractor. Then we have the camera over there. I don't know why they did that, but the other choice was to go up to the cage and image there, which I wasn't really that brave to do. But overall, it was quite an experience to do that. The following day, after JOI, we got to visit JPL. We have Glenn Orton here. This is, I wonder if you know this guy, David Ho-Tech. He makes collimators, laser collimators for different telescopes. He's actually from Taiwan. He's living in the US right now. And this is mission control. So it was quite an experience to be there. And yeah, finally I would like to thank Glenn Orton for helping me out. Yeah, this is my main contact in JPL, and he was the one who basically does the professional amateur collaboration for the JUNO spacecraft. And this picture was this is at the Rose Bowl in Pasadena, where everybody involved with JUNO was there for the big pictorial. Okay, so we'll do the Q&A.
Is it finished?
Yeah, it's done.
Okay. I think it's quite an interesting presentation by Chris for the very fundamental imaging skills and also to the latest JUNO mission. And in fact, I think many of you would be...
As you can see, after stacking, this is basically how the image looks like. And when you apply wavelets, there. Normally I would play here the initial layer and the step increments. Normally I would only do the first three. Now, how does this work? One, as you go higher, you go fine details. Here, more coarse details. Okay? So, fine, the higher you go, the finer the detail, it will sharpen. Of course, if you push one too high, the image will become very grainy. So you have to play. Yeah.
I played around with this for a while, and with that many sliders, and you don't know how much to push it over, I gave up.
Yeah, I can understand that. That's how I felt the first time.
Yeah.
Then I discovered that all you have to do is to do the first three.
First three.
Yeah, and of course, increasing the initial layer will also save you from pushing it too high. Okay, increasing from 1 to 2, and sometimes I use the step increment instead of 0. Look at what happens if I change it to 1. So you can play with it.
Yeah.
If you think this is too much, then you pull back.
Is this program just for planetary or?
This used to be the stacking software.
Yeah.
But AutoStacker is more, I would say, more gives better quality because AutoStacker uses what you would call a multi-point alignment.
Okay.
So instead of using the whole image, it will just get patches. If, let's say, this is sharp, this is blurry, it will throw away the blurry one and patch it with another.
Okay.
In which case, you have a higher chance of a sharper image.
That was my first question, is how do you stack the images? Because like you're doing deep space objects, you've got all these stars around there, you just pick some stars and it lines things up, and then you stack them. But with the signal changing like this, how do you get them to line up? So that
It's
other
actually pretty
program,
simple because AutoStacker is all you have to do is to open.
AutoStack.
Maybe Chris, you can also demonstrate how you select the point, select the features for stacking.
Actually, to be honest, I do it automatically.
That's my kind of program. I like it. Go button.
So this is what you do with the AutoStacker. When you open it, you see this one over here. Place AP grid. I'll just place that there. We'll align that.
Yeah.
And basically, the next thing you do, what I normally do, I drizzle my image by 1.5 times and basically estimate if the seeing is good, I would stack about 80% of my image. if the seeing is average, probably about 40%, half of it. If it's bad, probably 20-30%. So you can change from here and stack. That's all.
So your daily images you're showing on your website, are those stacked and processed?
Yeah.
Okay.
One thing that we do now is after stacking, there's a process what we call derotation. Now the problem we have with imaging planets is that, like Earth, they all rotate. Now the problem with rotation is that it limits how long you can capture per channel. Because if you capture too long, it will smear the image. So in case of Jupiter, with my C14, the most I can go is 30 seconds for red, 30 seconds for green, and 30 seconds for blue. But now after you mix it all up, normally this is what you get. It's a bit grainy. This is a single RGB capture with using my telescope. But what I normally do, there's a software called Hubble. What it actually does is that it will convert this from spherical to cylindrical. And if you have, let's say, multiple images, it will stack it on the central meridian. So it's like stacking on steroids. So you can actually, in the case of Saturn, I can stack up to 1 hour of data. To give you an example, because this is really very clear with Saturn. Oh, I need to process this. Having bad seeing or bad transparency is no longer an excuse of not having a good image, because, as I said, there's no more limit on how long you can capture data. So, example, in my case, if the seeing is good, transparency is good, I require only 3 RGB, then I can get a good image. When transparency is bad, depending on how bad it is, because sometimes you have to image through clouds. I go as far as 15 minutes, 20 minutes, and just derotate the hell out of it, and get a good image. To give you an example, I have an image last May, and it's one of those days where you want to kill somebody. What happened was that in my city we were having drought, and our city government decided to do cloud seeding while I was imaging Jupiter. I almost wanted to have a bazooka and just shoot that plane down. So transparency was horrible. But this is the image. All I did was I just took more image. Oh, here it is. This is what I got.
Very nice.
This image. But of course, it took a little more work. Instead of 4.5 minutes, 7 minutes. It took a little longer to capture, to get that image.
So the planets are very bright compared to galaxies and other objects. So why do you need a lot of aperture with planetary, what does the aperture give you? You've already got lots of brightness.
To make it bigger.
Bigger.
You know how big this is? This is about last May, it was about 40 arc seconds.
Yeah.
And you stretch it at on 0.60. Why? Because sometimes when you do the rotation, you'll notice if you don't place it at 60, one edge will be very bright. So the way to remove that artifact is to reduce the LD value to 0.60 or 70. 60 would be better. This is the for the limb darkening.
This is quite steady. This grade. It's quite
Yeah, it's steady. Yeah, you'll notice that you'll have a sharp, bright edge after derotation. Then it means that your LD value didn't drop it. So once you do the, I would suggest that you reduce that to 0.60 and just check it. Now, by the way, I would suggest you do it on an IPS monitor. It's gonna be, that's how you do it. Basically, you can see the shadow and everything. It's framed, and once it's done, all you have to do is to go back to the image and basically save it. So, what are you saving? You're not saving an image, but you're saving an image measurement file. So you do it with all your images. Now, one thing nice is, if you didn't change the orientation of your camera, you have to do this alignment only once. After you do the alignment, you just open, save, open, save, open, save, open, save, open, save. Then you have a whole stack of image measurement files. Then after that is the best part. Although I don't have enough data, I should have I'll probably work on it. You open all the image measurement. If you have 4, 5, 10, you open it up. This one you only have one, so this one then once everything is there, you make sure you want to save it on PNG, TIFF, or JPEG. I would suggest PNG or TIFF. Next is orientation, north up, south up. ALPO will say, oh, you have to do it south up. Professionals will say north up. Right now I do everything north up. Then after that, press compile. And you have a derotated image. So basically that's how you do it.
Any other question?